We're going to start a new chapter today, chapter 8. We skip over 5, 6, and 7. 1, 2, 3, no, 6 and 7. And we're going to do 8, and then we'll come back to 6 and 7. I thought the material that's covered in 8 is essential to understanding 6 and 7. So I think the authors got the chapters switched around. But these are the handouts that I want you to get hold of. Of course, the PowerPoints. I don't need to show you that one. But the review document looks like that. Get a little closer. Okay. And then in that same folder in Blackboard, we'll have the work problems. Then the review document also has a key in that folder. We'll cover chapter 8 today, and then we'll have a review on Tuesday. All right, let me get my pointer. Okay, chemical composition. Let's move along here. We always skip the table of contents because we're going to get there anyway. All right, first topic. What do we mean by counting by weighing? In fact, why do we need to do something like that? What do we mean? Counting by weighing. If we're dealing with a situation in chemistry where all the action is microscopic, can't see it. So we need some way to connect between the microscopic and the macroscopic world such that we can actually quantify what's happening on the microscopic level with tools and measurements that we can perform on our level. So this is one of the methods that we use to count objects that are that small. In order to do that, we need to know what is the average mass of individual objects. In our case, atoms, ions, molecules. What's the average mass of each one so that if we weigh them, we can determine how many of them there are. Okay. Here's an example. If we know that we have 1,000 jelly beans, right, that's not too many to count. It'll take you a while, but you can still count them. We know that not all of those jelly beans have the same mass. Right? There's just manufacturing variability will give you varying masses for each jelly bean. In fact, I've seen jelly beans that had 2 or 3 of them stuck together. So we want to find out the average mass of a jelly bean. Well, you could take the 1,000 jelly beans and just weigh them and divide by 1,000. But suppose you have 50 billion jelly beans, right? You can't do that. So what we do is take a representative sample of the whole and weigh that and get a mass. And then determine the average mass based on that sampling. Now, it's critical that your sampling be representative of the whole. If your sampling is biased in any way, it will affect the average value that you determine for one jelly bean. Let's say we take 10 jelly beans and we find out that here are the weights or the masses for each jelly bean. Right? They range looks like between 4.8 and 5.2 is the range. And then we add them all together, divide by 10, and get an average mass. Okay? So the average mass of a jelly bean we determine is 5 grams. If we write it this way, what does that look like? To me, it looks like a conversion factor, because we're saying that 1 jelly bean equals 5 grams. If you've got a conversion factor, then if you have one of these, you can find the other one. So if we have 1,000 jelly beans, we can find out how much they're supposed to weigh. But what we'd rather do is weigh the 1,000 jelly beans and use this conversion factor to determine how many of them there are. Suppose we don't know that there are exactly 1,000 jelly beans. Right? It could be 987, or it could be 1,025. So we don't know that. We just assume that we have 1,000 jelly beans. But if we weigh them after finding this conversion factor, we can determine pretty close how many jelly beans there are. All right, so if we, let's see. I feel like I'm missing a slide. Let's say we weigh those jelly beans and we find that they're, let's say 5.76 kilograms. Okay. If they weigh that much, can we use this value? Well, no, not yet, because they're the wrong measurements. That's grams and this kilograms. So how many grams is 5.76 kilograms? We move it 3 to the right. 5,760 grams. Now we're going to convert that to numbers of jelly beans. So we need our conversion factor. That's on the bottom. And that's on the top. So divide this value, 5760, divided by 5. And I get 1,152. Okay, so based upon that measurement, we actually have 1,152 jelly beans, not 1,000. Okay, so that's the concept of counting by weight. We need an agreed upon value for an individual jelly bean. Okay, now start thinking jelly beans, atoms, atoms, jelly beans. We need an agreed upon value for the average atom. But we're not ancient Greeks anymore, so we don't think that everything's made of the same atom. We know based on John Dalton's theory and subsequent proofs that every element has different atoms. So each element is going to have a different mass for its atom. Okay. I don't even know what that means. How'd that slide get in here? Another example with marbles, right? So I'm not going to beat this horse anymore. If you weigh all the marbles in your pile and they're 394.8 grams, then you take 10 of them and determine the mass for 10, then you can use that as your conversion factor. You don't have to say one marble weighs something. You can actually just say, if we have 394.80 grams, then you know the conversion factor is mass marbles, and the mass is 3,760, and that's 10 marbles. That's a perfectly valid conversion factor. Just divide this into that one times 10. Right? Now, the way this is worked out on the board, we found an average mass first, which would be what you would expect for using this concept in the case of atoms. We would do that. Okay. Now, how about atoms? Well, we know that atoms are very, very small. A little weight each. We don't have balances sensitive enough to weigh one atom. At least, I don't have any. And in the typical laboratory, you need billions of atoms to have enough to actually determine the mass of that pile of atoms. So since they're very small and they're huge in number, we can't even count them. Most people don't have the technology to count individual atoms. It can be done. But for practical chemistry, we need to be able to use something that we typically have in the laboratory, an analytical balance that will determine the mass of whatever the element is. And then you convert that into numbers of atoms. Why would we want to do that? I mean, go to all that trouble. Isn't mass good enough? As it turns out, no. Chemists and physicists in Europe in the middle 19th century found out that knowing the mass of reactants and mass of products didn't solve their problems. When a reaction went wrong and all they had to go on was mass, they were completely flummoxed. They had no idea how to fix the problem. So university professors were just flopping around trying to explain things to their students. And companies who had chemists in their employ were shepherding their chemical processes to make products, and they were falling apart too. As it turns out, if you don't know how many atoms of each element are part of a reaction, then you don't know anything about that reaction. So that's why we need numbers of atoms, numbers of molecules, in order to properly describe a chemical reaction. So, we've got this unit of measure called the atomic mass unit. One atomic mass unit, 1 AMU, has been determined and fixed as this mass, 1.66 times 10 to the minus 24 grams. Now, they didn't just pull that number out of thin air. It's based upon a standard. And the standard is the carbon-12 isotope. Okay? You need a standard. Everybody's got to agree on something that's fixed, and everything else can be referenced to it. So if we take this as our standard, and we say that atom of that isotope has a mass of 12.0 atomic mass units. Okay? That's our standard. As many zeros as you want. It's the only isotope, an atom in the periodic table that has a fixed whole number mass. Everybody else is referenced to that, so they're going to be fractional masses. So if this carbon isotope, this atom, weighs that many units, and we can determine how much that isotope weighs, or what its mass is in grams, then we can associate that with one atomic mass unit, just about 12 into it. And that's where this number comes from. Okay? Now, the The next problem is that we know that naturally occurring elements are composed of a mix of isotopes. Carbon does. This may be the standard, but that's only one isotope of carbon. So if you isolate carbon from nature, it's going to have this one, plus it's going to have some of this one. It might even have some of this one. Right? This one is a stable isotope. It doesn't change. No radioactivity. That one is stable. That one is radioactive. And it's a minor component, 0.01% of the total. So we can virtually ignore this one. But this one is a substantial percent. It's like 1.11% of the total. So we have to consider both of them. So what does that do for the atomic mass of a naturally occurring element? Remember, when we're counting by weighing, we're depending upon an average value for our atoms. Well, if this one's going to be 12 and that one's going to be 13 point something, then the average value has to be weighted for those abundances. So most of them are this. So the value that is reported for an average carbon atom will be close to 12, but it'll be influenced by the numbers here. Okay? So that's why the average value that you'll see in the periodic table for carbon, rounded off to 2 decimal places, is 12.01, because it includes the influence and the abundance of that other isotope. So now as chemists, if we isolate carbon, or we introduce carbon into a reaction, we don't have to worry about the isotopic mix. That's already been factored into the average value. And by the way, that value, 12.01, is not a simple arithmetic average. It's a weighted average. Kind of like determine your grade point average, right? This course is worth, 4 credits. So if you get an A here, it carries a whole lot more weight than an A in a course that's only worth 2 credits. So when you calculate your GPA, your average there is weighted more by the 4 credit course than it is by the 2 credit course. And that's the similar concept that we use in calculating these weighted averages for all of the elements in the periodic table. Okay. So if we have, let's say theoretically speaking, if we know we have 431 atoms of carbon, what's the mass in atomic mass units? Well, we don't know. It didn't say that there were carbon 12s. So we can't say that's 12 units per atom and multiplied by 431. We have to assume that it's a mix. And the average is 12.01. So we multiply 12.01 times 431. So it's still dimensional analysis, conversion factor time, 431 atoms. And the average atom has a mass of 12.01 atomic mass units. So we just multiply 12 times that cancels. 12 times that value, and we get 5,176 atomic mass units. Now, believe me, I'm getting to some more practical application. We're on the way there. We just haven't arrived yet. Because we don't have a balance that'll measure in atomic mass units. It just does not exist in most chemistry labs. So We're going to get there eventually to where we can measure these things in a familiar unit of measure, like grams or kilograms or micrograms or whatever the case may be. Okay. How about 75 atoms of aluminum? Now, the question is, what's the total mass in atomic mass units for this many atoms of aluminum? Do we have all the information we need? Well, what's the question? We want to end up with a total of atomic mass units for aluminum. Right? So what do we need? Well, we've got 75 atoms, right? That's given. Okay? We need a conversion factor that will get rid of atoms and leave us with atomic mass units. So where do you go for that information? The periodic table. You look up what's known as the molar mass or the atomic mass in the periodic table. And it's off camera, but I'm going to look at it anyway. 26.98. Per atom. Okay? Just multiply those numbers together. And with that many atoms of aluminum, you have 2,024 atomic mass units. Now, we can convert those to grams, right? We have a conversion factor for that. Was it 1.66 times 10 to the minus 24 grams? We could convert that to grams if we wanted to. Okay. So now we come to the concept of the mole. The mole is simply a number of things. Now, it's derived from the real world, and it's defined in these terms. If you have 12.01 grams of carbon, naturally occurring carbon, pure carbon, then it will contain 1 mole of carbon atoms. And there's a number associated with that. 12.01 grams of carbon is equal to 6.022 times 10 to the 23rd atoms, which is equal to 1 mole. Funny thing about the mole, if we write out the whole name, that's mole. But if we want to shorten it, abbreviate it, you drop the E. I never could figure that one out. Seems like it's hardly worth the trouble. Okay, so anytime you have a mole of something, you have 6.022 times 10 to the 23rd of them. That number. So for our purposes, that could be atoms, could be ions, it could be molecules, it could be formula units, like sodium chloride, which is not a molecule. Sodium chloride is the simplest whole number ratio of sodium atoms to chloride ions in the solid. It could be 6.022 times 10 to the 23rd chickens would be 1 mole of chickens. It's just a number. But it's a useful number because if you have that many atoms of any one of the elements in the periodic table, you know that you have that mass that's reported for that element. The atomic mass of that element will contain exactly 1 mole of those atoms. Now we have something useful, something we can sink our teeth into, something we can measure in the laboratory. This is called Avogadro's number. Now, Avogadro never measured the mole. This is an honorarium. He is honored with that name for this number because of his hypothesis that was eventually proved correct and allowed scientists to relate mass and numbers. Remember Avogadro's hypothesis, his theory? Remember what he said? If you have two volumes here of gases, it doesn't matter what kind of gas is in there, as long as it's a gas in each one. If the volumes are equal and the pressure inside each one is equal to the other, and the temperatures are equal, then it must be that there are equal numbers of particles in each one. And I use a little n to abbreviate that. And from now on, that little n is going to stand for moles. We have the same number of atoms or molecules or particles of any kind, as long as they're gases, under these conditions. And that's how we relate one element to another. Suppose we had gaseous carbon-12 in here. It would have to be a high temperature, but it can be done. And then the other gas is, well, I don't know, helium, right? Which has a mass number of 4. Now that's one isotope of helium, of course. We can relate the weights of this fixed value at 12 atomic mass units to this one and determine that this one is in the neighborhood of 4. How do we know that? Because we have equal numbers of atoms in each one, but they have different masses, right? This one has a mass that's 3 times this one. How do you explain different masses when they're all the same numbers of particles, the same numbers of atoms? The only explanation is that each atom has a different mass than the other one. So this one must be 1/3 the mass of that one. Okay? Let's say, for instance, we determine that this one is 120 grams. This one has to be 30 grams. Oh, excuse me, 40 grams. Okay? That's how you relate one element to the other in terms of their mass. So now we have our fixed, and we can do this for a number of different elements, and then we can use those elements in a more convenient situation to compare with other elements. Now, it's difficult to get carbon into a gas, but once you do, and you can compare a number of other gases, then you can use those comparisons to sort of leapfrog for the other elements. Okay. So that's how we relate atomic masses of one to the other based upon carbon-12 as our standard. Okay. So we've got these conversion factors that you can use. Right? 1 mole equals that many atoms, or that many atoms equals 1 mole. For carbon, that many atoms weighs this much, or that weight gives you that many atoms. So you've got multiple conversion factors that come out of this whole discussion. Okay. By the way, that's why we call that value in the periodic table, where you see a different, not the atomic number, but the other value that we refer to as atomic weight or atomic mass. It's also called molar mass, because that's the mass of 1 mole of that element's atoms. All right. And this just illustrates the fact. If you have a mole of each one of these, you have different masses. Right? Gold is pretty heavy. In fact, it's the heaviest one on the list. So a mole of gold atoms is going to weigh 196.97 grams. One atom of gold weighs 196.97 atomic mass units on average. Right? You will never find one atom of gold that has a mass of 196.97 atomic mass units. It doesn't exist because it's a weighted average of the naturally occurring abundance of the different isotopes. All right. Suppose we use what we know now to answer this question. What's the number of copper atoms in 63.55 gram sample of copper? So we know we have copper, that's given, and we know our sample is 63.55 grams. So if we're going to convert that to the number of atoms, we need to determine how many moles that is first, and then we can springboard the moles into numbers of atoms. But guess what? If you look it up in the periodic table, 63.55 grams is 1 mole of copper. So that's 6.022 times 10 to the 23rd atoms. You don't even have to do a calculation. It's right here. Okay? Trick question. Just to see if you're paying attention. Okay. This is kind of a dumb slide, really. One atom of copper, what's the mass of one atom of copper? One atom of copper is not going to weigh grams, not that many grams. Right? So if you see this question on a test, you can instantly go to E as your answer. Because we know the atom is going to be much, much less than any one of these. Okay, but it can be calculated. Right? One copper atom, we can relate that to how many moles does that represent? Right? It's a fraction of a mole. And then this converts moles to mass. That's the molar mass. Whenever you see grams and moles in that relationship as a quotient, think molar mass. And then we can actually calculate this value. Right, if I'd been thinking, actually, I took this from the authors of the textbook. I should modify it and put different values in here that are on the level of an atom. Then you'd actually have to calculate it. Okay. Calculate the number of iron atoms in a 4.48 mole sample of iron. In this case, does it matter that it's iron? No, because the conversion is moles to numbers of atoms. And that's good for any element. And we can have a mix of elements. We can have 4.48 moles of iron, aluminum, vanadium, any of the elements mixed together. If we know that many moles of the total, then we can calculate the number of atoms. It doesn't matter what they are. Okay? So we just use this as our conversion factor. Cancels the moles and leaves us with atoms. Okay, so there are a lot of atoms there. Let's see, what's 10 to the 24th? Let's see, 10 to the 6th is 1,000,000. 10 to the 9th is 1,000,000,000. 10 to the 12th is a trillion. 10 to the 15th is a quadrillion. You know, just keep going. All right. Now, suppose we have a sample of 26.98 grams of aluminum. we're comparing this that sample, and we want the mass of gold that has exactly the same number of atoms. Well, it's really not that difficult, because if you look on your periodic table, 26.98 is the molar mass of aluminum. So you know you have 1 mole here. So all you need is a mole of gold, and you can get that from the periodic table too. Right? And it turns out, since that's 1 mole, then 1 mole of gold is approximately 197 grams. It's actually, that's right, rounded off to 2 places, it would be 197.00. Okay? They have the same number of atoms, but their masses are different. Aluminum is a much lighter atom, smaller, lighter atom than gold. Okay. Now consider this. Suppose you have a 100-gram sample of each one of these elements: magnesium, zinc, and silver. Right? You have equal masses. Right? So what's the first thing that comes to mind? They're not the same number of atoms, because each atom has a different mass. So then the question is, which one has the greatest number of atoms? Remember our example comparing carbon and helium? Which one of those had the greatest number of atoms? Well, they have the same number of atoms, correct? With our example. But if we have different masses, if we have the same mass, a 100-gram sample, how do we get 100 grams of silver? You have a certain number of atoms. We'll give you 100 grams. How about zinc? Zinc will take more atoms, because zinc is a lighter atom. It takes more of them to make 100 grams. And magnesium is even lighter than those two. It takes many more atoms of magnesium to make 100 grams, because it's a lighter atom. Okay? So this is the molar mass of magnesium. This is zinc. This is silver. So it takes many more of magnesium to make the same mass as the other two. Okay? That was a concept check. What if we have this situation? I'm going to put this one on the board. So we have 107.9 grams of silver. We have 70 grams of zinc. And we have 21.0 grams of magnesium. Now the question is, put them in order of numbers of atoms. Do we have to calculate the numbers of atoms using Avogadro's number? No. If we're going to compare numbers, all we need is that more convenient unit of measure, the mole. So, 107.9 grams of silver. Let's look on a periodic table and see what that is in relationship to a mole. Actually, 107.9 grams of silver is 1 mole. Okay? How about zinc? 70 grams of zinc. Let's look at the periodic table again. Zinc is 65.38 grams per mole. This is greater than a mole. And we've already seen magnesium. I think it was 24.3. Yeah, 24.31 grams is a mole of magnesium, so it's less than a mole. Now, since we only have 3, that makes it easy. From greatest to least, this is the greatest, zinc, in numbers of atoms. Then we have 1 mole of silver, and then we have magnesium. Okay. And you can knock that out in 15 or 20 seconds. I just illustrated here what we did in our heads, right? 1 mole, greater than a mole, less than a mole. And that makes the order B, zinc, A, silver, and C, magnesium. Okay. So this is just this is a statement of how you solve problems. This works for any type of problem, actually, not just chemistry, not just physics or the sciences, any kind of problem. What's the question? Right? Sometimes that's the hardest part of a problem. What is being asked? What does the question ask for? Most test questions are fairly simple, right? But in real life, sometimes finding out what the question is the hardest part. But you got to know what the question is or you'll never get the answer. And then once you know what the question is, you need to map out a strategy for solving that problem, to answering the question. Sometimes it's really simple, sometimes it's complex. And if you have a complex question, you need to break it into pieces. It's kind of like cooking, right? Cooking a dinner. Sometimes you need to prepare a component over here and then a component over here and time them just right so that when you put them together, you get the final product. So you have to break it into pieces, manageable pieces to solve some problems. Then, of course, you need to ask, do I have enough information to solve the problems? If the information is not given in the problem itself, you may have to go looking for it. One place that in chemistry we look is the periodic table. Periodic table is your best friend. It's got tons of information in it. And then the way I present materials, I give you that useful information, right? So learn how to use that document, that part of the document, useful information. And if you work enough problems, a lot of these bits and pieces of information are going to be memorized just out of habit, just doing the problems over and over again. Like I said, if you're bored doing a problem, then you probably know it pretty well. And more than likely, you've memorized some things that you would expect to have to research if you were only seeing the problem for the first time. But if you've seen that problem before, you may have everything you need right up here. All right. And then once you solve the problem, you think you solved the problem, ask yourself, does this answer make sense? Right? It's kind of like that question earlier with how much does a copper atom weigh? If you calculate the value for a copper atom and it comes out in grams, like 60 grams of copper for one atom, then you know something's wrong. I mean, that you should have alarm bells going off in your head. Okay, I mentioned molar mass before. It's simply what is the mass of a mole of atoms of a particular element. That's the molar mass. But it can be extended from atoms to compounds, molecules, formula units. We can determine the molar mass of a formula or a bona fide molecule or any compound if we know the individual molar masses of the atoms that make up that compound. Okay? So nitrogen, you can look it up in the table, rounded off to 2 places is 14.01 grams per mole of nitrogen atoms, naturally occurring nitrogen. So we've taken into account the natural abundance of the different isotopes of nitrogen in reporting that value. How about water? Okay, water's a molecule. Right? You can look at it like this. 2 hydrogens, 1 oxygen. So what's the molar mass of water? Well, if you have 1 mole of this, right? How many moles of oxygen do you have? Well, for every 1 mole of this, you have 1 mole of oxygen, correct? So this is 1 mole. How many moles of hydrogen do you have? We actually have 2, right? This is 1 mole, and this is 1 mole. So you have 1 mole of oxygen, 2 moles of hydrogen. And we know what those values are from the periodic table. Oxygen is 16 grams per mole. Hydrogen is 1.01 grams per mole, but we have 2 of them, correct? So we actually have 2.02 grams per mole. This is oxygen, this is hydrogen. Add them together, you have 18.02 grams per mole of water. Okay, that's where that comes from. And it works for any compound. As long as you have the formula for the compound, you can determine the molar mass of that compound. Whether it's a molecule or whether it's an ionic compound like sodium chloride. We know sodium chloride is not just that. It's an ionic crystal matrix of sodium ions and chloride ions. But this is the simplest whole number ratio of sodium and chloride ions. So for that formula unit, we can determine the molar mass, 1 mole of that formula. All right, here's a big one. Okay. How do we do this one? Barium nitrate. That's why it was so important to learn how to write compounds. In this case, by balancing charges. Barium is an alkaline earth. It's in the 2nd group, which means it has a 2+ charge. So if barium has a 2+ charge, and the polyatomic ion nitrate, NO3, has 1- charge. So you need 2 of them, correct? You need 2 of these to go with 1 barium. That's the simplest whole number ratio of barium ions to nitrate ions. Barium has a mass, let's see, there it is, 137.33 grams per mole of barium. In this molecule, how many nitrogens do you have? 2, because that subscript propagates through the nitrate formula. We have 2 nitrogens, and we have 6 oxygens. Okay, so just multiply these out, multiply those out, add them all together. And that's where you get 261.35 grams per mole of that formula unit, right here. So if you have a solid barium nitrate in a jar, and you determine that you have 261.35 grams on your balance, you know that that's a mole of that compound. Okay. Let's see. I don't know that this might be confusing. I mean, it's true. That formula is true. But I don't like just memorizing formulas. I like to know how they're put together. This one was put together, if you have so many moles of compound, and you multiply it by a factor, grams per mole, then the moles cancel and leave you with grams. And that's where this grams comes from. So I follow the units. If the units of measure don't work out in your formula, then there's something wrong. Doesn't matter what the numbers are. If the units don't work, then you can forget about the numbers. Okay. So that's all I'm going to say about that slide. How about the molar mass of nickel-2 carbonate? Now we've got to write the compound. If you can't write the compound from the name, then you'll never determine the molar mass. So nickel-2 carbonate has what? Nickel with a 2+ charge. Correct? That's the way the name is written. That's a transition metal. It has the possibility of multiple charges, so it's a type 2 compound. And then you have carbonate. So we have to know what carbonate means. Carbonate is a polyatomic ion with a 2- charge. So you only need one of each. So if we know the molar mass of this one, the molar mass of that one, 3 times the molar mass of this one, add them together, that will give you the molar mass of nickel carbonate. Right? There's the compound. Here's nickel, here's carbon, and here's 3 times oxygen. Add them together. All right. So let's see if we can make it more complicated. If we have equal moles of N2O, dinitrogen monoxide, aluminum nitrate, and potassium cyanide, equal moles of each sample. Rank them from least to most number of nitrogen atoms in each sample. Well, if you have equal moles of the compound, all you need is which one has more nitrogens in its formula. Because 1 mole of that is 2 moles of nitrogen. 1 mole of that is 3 moles of nitrogen. 1 mole of that is 1 mole of nitrogen. So the least would be this one, right? Either this one or that one. And then the next one would be this one into, oh, there it is right there. And then the last one is aluminum nitrate. It has the most number of nitrogen atoms in equal molar sample sizes of those 3 compounds. Okay? All right, I need to get a move on here. So I've got a couple of topics to get through that I haven't not even got there yet. So we have a 100-gram sample of each of the following: water, dinitrogen monoxide, this one is propionic acid, and carbon dioxide. So you don't need to know how to name this one. This is an organic compound, and we haven't covered naming organics here, so don't worry about that. Greatest to least number of oxygen atoms. When you're faced with a situation like this, you've got to do a similar calculation on each one of these compounds. Then I set up a Henry Ford assembly line. So I would put water, dinitrogen monoxide, let's see, C3, H6O2, and CO2. Okay? We have 100 grams of each. right? So we know we're starting with the same amount of each one. Actually, there's an extra zero up here. Okay. Now we want to convert those to what? Well, if we're going to say which one has the greatest, order them from greatest to least number of oxygen atoms, we can't say anything about the number of oxygen atoms until we know how many moles of each compound there is. Right? Then we can relate the number of moles of the compound to how many oxygen atoms that represents. The reason I say that is 1 mole of water is 1 mole of oxygen because there's only one for each. Dinitrogen monoxide is 1 to 1. Propionic acid is 2 to 1. So moles of compound times 2 will give you the moles of oxygen. And same thing for carbon dioxide. So we need to convert these to moles of compound. Here's the assembly line. Right? We're doing the same operation for each one. We need grams on the bottom, moles on the top. That's what we want, moles of compound. So what value is going here? Well, they're different for each one. These are molar masses. We've done water before. We know that one is 18.02. Dinitrogen monoxide. Right? This is 2 times 14.01, correct? For nitrogen. And then 1 oxygen. So what would that be? Say 2, 0, 8, 14, and 1 and 3, 44.02. Okay. This one takes a little more work. I need my calculator for that one. So how much does carbon weigh? 12.01. Remember that? 3 of those. Okay. 36.03. How much does hydrogen weigh? 1 mole of hydrogen is 1.01. So 6 of them is 6.06. Add that in. 2 oxygens. 1 oxygen is 16, so 2 of them is 32. Round it off to 2 decimal places. So that's 74.09. Okay? Carbon dioxide. Carbon's 12.01, correct? 12.01. And 2 oxygen is, again, 32. So that's 44.01. There you go. Now what we need to do is divide each one of these into 100. Well, why don't we chain them together? We got rid of the grams, right? Now we got moles of compound, right? Each one of these is compound. So what's the relationship of moles of compound to moles of oxygen? Right? Moles of oxygen. Okay? Compound, compound, moles of compound. Right? This is 1 to 1. 1 mole of oxygen for every mole of water. Same thing for a decimal. This one has 2 for each one. And this one has 2 for each one. So now, we've canceled that. And now we just do the calculation, right? 100 divided by 18.02 times 1 is 5.55 moles of oxygen in 100 grams of that sample. How about this one? 44.02 divided is 2.27. And this one is, let's see, divided by 74.09, right, times 2. 2.70. Okay, and the last one, 100 divided by 44.01 times 2 is 4.54. Okay, so which one has the, from greatest to least? So this is the first one, this is the second one, this is the third one, and this is the fourth one. Okay. Now, what you'll notice here is I went ahead and calculated numbers of oxygen atoms. You don't have to do that, not when you're putting them in order. As long as you know the number of moles of each, you can tell the order. Right? So there's the order. Water, yep, number 1. Number 2 is carbon dioxide, yep. Number 3 is propionic acid, and dinitrogen monoxide is the last one. All right. So that's my Henry Ford analogy. Assembly line. And doing it that way also organizes your calculations. You're less likely to make mistakes. And if you do make a mistake, it's easier to catch them. How many grams of fluorine are contained in 1 molecule of boron trifluoride? Well, since we're running a little short on time, I'm going to see, yeah, the calculation is given here. 1 molecule of boron trifluoride is, you have 3 atoms per molecule. So now we know how many atoms of fluorine contained here. Right? Cancel that, 3 atoms. Now, if you have 1 molecule of boron trifluoride, you have 3 atoms. And 3 atoms is how many moles? That's what we're doing here. We're converting atoms of fluorine to moles. And once we know the moles of fluorine, we can convert to grams using the molar mass of fluorine, which is 19.00. So that's how much, or how many grams of fluorine are in 1 molecule of boron trifluoride. It's dimensional analysis. It's conversion factor time. Like I've said before, a lot of chemistry problems you can solve by dimensional analysis, conversion factors. You know, as long as it doesn't violate any physical rules, any laws, then sure, go ahead. Okay. What do we mean by mass percent of an element? What we're talking about here is what's the percentage by mass of an element in a given compound? So if you have 100 grams of the compound, how many grams of it is that element? That's percent, right? Parts per 100. Grams per 100 grams. And that's usually what we, well, that's exactly what we mean by mass percent. Okay? Mass of the element in the compound plus the mass of the compound, divided by the mass of the compound. Now, there are 2 ways to get that. You can do a theoretical way. If you know the formula for the compound, you can calculate the mass percent. Or if you go into the laboratory and take the pure compound and do some analysis, you can generate a report that says this is how much of each element is in this compound. We're going to do the theoretical one first. Right? So for iron oxide, iron 3 oxide, how do you determine what the mass of the compound is? Because all we have is the name and the formula. Well, let's assume, which is perfectly valid, let's assume that you have 1 mole of that compound. How much mass would you have of each? If you have a mole of iron 3 oxide, you would have this much iron, right? Mass of the element. And you'd have this much of the compound. You'd have the mass of the iron plus the mass of oxygen. Right? Notice this is in the numerator and the denominator. So there's your oxygen, there's your iron. That's the total molar mass. And this is how much of the iron is in that compound times 100. 69.94% theoretically is the mass percent composition of iron in that compound. Okay, what about this one? This is morphine, derived from the opium plant. We know it's been determined its molecular formula is C17H19, 1 N and 3 oxygens. So what's the percent by mass of carbon in this compound? Well, you need to add up the total mass, right, for 1 mole of that compound, and then say how much of that is composed of carbon. Right? So here's your carbon. Here's your carbon also in the total, right? There's your hydrogen. There's your nitrogen, and there are your 3 oxygens. And the percent of carbon in there is 71.6%. Okay, we got the same 100-gram sample of each of the following, which has the highest, ranked highest to lowest percent oxygen by mass. Okay, I'm not going to do this one because it'd take too long, but you use that same assembly line process and you calculate the percent oxygen for this one by the method we just showed you for iron oxide and for morphine. You say 16 divided by 18.02 times 100. And that's your percent oxygen. Do that for each one and then rank them. Right? And the most oxygen is water by percent, by mass percent. Does that make sense? Well, look, that molecule is mostly oxygen by mass because hydrogen weighs almost nothing. So yeah, it makes sense. This one has the highest percent by mass of oxygen. And then carbon dioxide, and then, well, then the others. I clicked too far. Okay, now we're going to put this information to practical use. The second possibility, as I mentioned, is you go in the lab and you analyze the sample and determine the percent by mass of each of the components, each of the elements in that compound. We're going to use that information to derive the true molecular formula for the compound. We go through 2 stages. First, we determine the empirical formula. The empirical formula is the simplest whole number ratio of atoms in that compound. That's not the molecular formula necessarily. It's just the simplest ratio of numbers of atoms in the compound. Okay? For instance, if we know that the compound is benzene, okay? What's the simplest whole number ratio? What can you divide each of these subscripts by that will simplify them further? Divide by 6. 6 into that one, 6 into this one gives you CH. This is the empirical formula. But how about acetylene? Right? The gas used in torches. Divide by 2. It has the same empirical formula. Okay? So if you determine the empirical formula from analysis percent mass analysis of a compound, this is not going to tell you which one is which, right? You need some more information. Okay? And if we write it like this, and we say there needs to be something here, something here. In this case, the multiplier is 6. And in this case, the multiplier is 2. So if you say 6 times 1 and 6 times 1, you have this compound. If you say 2 times 1 and 2 times 1, you have that compound. So what we're looking for, transitioning from empirical formula to molecular formula, we're looking for this multiplier right here. So here's the key. What is the empirical mass of 1 mole of this formula? Right? That's not the compound, but that's a representation. That formula says the empirical formula is 12.01 plus 1.01. So it's 13.02 grams per mole of CH. It's the same for both of them. Okay? So, but what's the mass of the actual molecule? Well, 6 times 12.01 for benzene, and then plus 6 times 1.01. So that's 78.12. So this one is 78.12 grams per mole of this formula. What's the relationship between this one and that one? 78.12 divided by 13.02 equals 6. That's exactly the number we need here to go from this one to that one. How about acetylene? Well, it's 2 times 12.01, which is 24.02, and then 2 times 1.01, which is 2.02. That's 26.04. 26.04 grams per mole. Right? What's the ratio of this one to that one? There you go. So now that says the information that we need after we determine this for our compound, the information we need is the true molar mass for the compound. Then if we take what I call the empirical weight for this formula, divide it into the true molar mass, then we get our multiplier. So that's where we're headed with this calculation. All right. So in this case, let's take this example. Let me see how much further I've got to go. If I can spend time on this or if I need to shorten things up. Okay, we'll take time for this one. A gaseous compound has what? Carbon and hydrogen. That's it. Nothing else. Right? How do we know that? Well, usually, if a chemist is presented with a pure compound, he or she will do a qualitative determination to see what elements are there. Right? And there are various tests you can perform and find that there's only carbon and there's only hydrogen. Right? If there are only those two, then that will help you determine what type of analysis you need to perform. So if we know that we have 83.65% carbon, by mass, then how much hydrogen do we have? Well, we have 100 minus that, don't we? (16.35%). Okay. But remember, percent is a dimensionless number. All it says is parts per 100. Okay. If you happen to know what they mean by parts, in this case, we mean grams. Grams per 100 grams of sample. So that means that this is 83.65 grams of carbon per 100 grams of sample. We can't use that to determine the ratio of atoms because there are no units there that we can convert. But if we assume the sample is 100 grams, for a 100 gram sample, we have 83.65 grams of carbon. And we have 16.35 grams of hydrogen. Now we can go somewhere. Because remember, the empirical formula and the molecular formula are ratios of atoms, not ratios of mass. We have to convert to moles of each to get the proper ratio. Now, this ratio of mass is true, right? Proust said that. He said that this is definite composition. That mass ratio to this mass is always the same for that compound, no matter where it comes from. But that doesn't help us solve the problem. It just says we have this ratio of mass. If we convert these to moles, then the ratio of moles will also be a constant. So now we need to convert to moles. Right? For carbon, it's 12.01. For hydrogen, it's 1.01. Right? So we're going to do that intermediate calculation first because we need to take a look at the ratio. And we know this is not going to be a whole number. And that's what we're looking for. Right? The subscripts of the elements in a compound need to be whole numbers. So let's do that calculation. 83.65 divided by 12.01 is 6.965. 6.965. That's moles of carbon. And 16.35 is 1.01 divided by that is 16.19. 16.19 moles. Okay. Now, how do you get whole numbers out of that? The ratio is true. This number of moles of carbon to this number of moles of hydrogen is true. But we want to convert it to whole numbers. Think back to math courses. If you do the same thing on both sides of the equation, like divide or multiply by the same value, then you still got the same ratio. So if we divide this one, let me do that calculation. Yeah, that's right. That's right. If we say 6.965 here and 6.965 here, divide both of them by the same number. That's equal to 1. And this is equal to 6.965 is equal to 2.3. 2.32. We're getting closer. One of them is a whole number now. Say this one is very close to a third right here. So how do you get rid of a third? Say this is like 2 1/3. You get rid of the third by multiplying that number by 3. If you multiply by 3, you get rid of the third. So if we say 3 times both of them, and that gives us 7 to the nearest whole number. Now, it's okay at this point to round, as long as you round your number that you're rounding is very close to the next whole number. So our ratio is carbon 3, hydrogen 7. Now, what is that? That's the empirical formula, the simplest whole number ratio. Now, oh, that's all it asks. Just do the empirical formula. Okay. Oh, I've got slides that are giving you step by step. That's fine. Okay. So there's the empirical formula for that compound. All right. We would have to be given the molar mass for the actual compound in order to make the transition from this to the molecular formula. Let's see, is it going to do that for us? Yeah, okay, it's coming up. Okay, so now, the molar mass of this compound, if we say 3 times 12.01 and 7 times 1.07, add them together, you get 86, excuse me, no you don't. What do we get here? 3 times 12.01 plus 7 times 1.01. Right, add those together. Let's see, that's 36.03 for carbon and 7.07 for hydrogen is 43.10. So 43.10 grams per mole of empirical formula. Okay? But we're also told that the actual molecule has a molar mass of 86.2 grams per mole. So if our multiplier is 1, that value should be 43, but it's not. What if our value here is 2? Then it should be 86.2 grams per mole. That's what it is. So our multiplier is 2, and the molecular formula then is C6H14. Okay? That's probably hexane. You don't need to know that. I just recognize the formula. Okay? We just ratioed the true molar mass against the empirical mass. All right, let's see. Do we have time for this one? It's the last one. We should be able to finish this one. We're going to use the same method. And notice we're given, well, it's asking first what's the empirical formula, and then I think on the subsequent slides, yeah, on subsequent slides, we're told the molar mass of the compound, so we can ratio and determine what that multiplier is. So let's run through this one real quick. Adipic acid, 49.3% carbon. Carbon. 6.9% hydrogen. And 43.8% oxygen. Okay, so we know what to do. assume you have a 100-gram sample, so 49, let's make it simple. Save time. Just convert all those to grams. Okay. There you go. 1, 1, 1. Carbon is 12.01. Hydrogen is 1.01. Oxygen is 16.00. Okay. So we should be able to knock these out pretty quick. 49.3 divided by 12.01 is 4.105. That's moles of carbon. 6.9 divided by 1.01 is 6.832 moles of hydrogen. And then oxygen is 43.8 divided by 16 is 2.738. 2.738 moles of oxygen. Okay? Now we have our fractional molar ratio of atoms. We need to convert to whole numbers. First step, take the smallest one and divide through each one by that same number. All right, this one's obviously going to be 1. Hydrogen is going to be, let's see, 2.50. And carbon is going to be, let's see, divide this into it, is 1.50. Okay, we're getting close. Now this is a half. How do you get rid of a half? Right? This is 1.5 times 2, right? Means 2 plus 1 is 3. Right? So we know this one is times 2 times 2 times 2. Now we have 3. We have 5, we have 2. So our empirical formula is carbon 3, hydrogen 5, and oxygen 2. All right, so we need to find the multiplier. Well, let's finish this off first. All right. Here we go. Now we're told the actual mass is 146 grams per mole. So whatever this is, times its multiplier is equal to 146 grams per mole. We need to find that multiplier. So what about this? What's the empirical mass? Well, let's see. Carbon is 12.01 times 3. Hydrogen is 5.05 because it's 5 times 1.01. And then oxygen, 2 times 16 is 32. Add that, 73.08. 73.08. Right. So you can probably inspect those and see that the multiplier should be 2. But if you have numbers that are a little more difficult to fathom in your head, just take this value, divide it by this value. And you get 1.9978, which is approximately 2. So there's your multiplier. So now the molecular formula is going to be C6H10O4. Oops, there it is. Okay, that's how you do it. Any questions? I've been talking straight for however long this class has lasted. And nobody's interrupted me, so I assume that you're soaking it all in. Plus, it's recorded. If you want to go back and look at it again. It'll just take me a couple of days to get it processed and uploaded. Okay. Any questions? What we'll do, see, it's Thursday, Tuesday, is we'll have a review based upon that review document. Okay.